All right, so we're going to learn about something called implicit differentiation in this formula. So, as we're going to see, this tool will help us find the derivatives for on the back, the log function and the natural logarithm function. But it also allows us to find the derivative in air quotes of relations that aren't functions. So we'll be able to. So in our first example here, this circle is not a function. It does not pass the vertical line test. Between -2 and 2, if you plug in a value of x, you get two values of y. So it's not a function, so you can't say f of x equals, describe this circle, and take its derivative. But we can still get an expression for the slope of the tangent line at any point on that circle. And I will show you how. So the idea is starting with the equation of our circle. This circle has a radius of 2, center at 0, 0. So it's equation x squared plus y squared equals 4. That's from your grade 10 math course. But we're going to start by differentiating both sides. Differentiate both sides. So I'm going to write it this way. We're going to take d by dx of x squared plus y squared. And we're going to take the derivative of 4. So if x squared plus y squared equals 4, then when we take the derivative of both sides, everything is still equal. So right side's easy. The derivative of 4 is just 0. On the left side, the first part is no problem, taking the derivative of x squared. That's just 2x. And to take the derivative of y squared, we just simply use our chain rule. So differentiate the outer function, which is y squared. So bring down the 2, leave the y alone, take 1 off the exponent. So that gives us 2 times y. And then multiply by the derivative of the inside, which is y. The derivative of y with respect to x, we'll just write as dy by dx. So we've differentiated both sides and used the chain rule. And now we'll just rearrange and get dy by dx by itself. We have the space here, so I might just do this in a couple of steps. So we have 2y. We'll bring over the negative 2, the negative 2x. And then we have dy by dx by itself. It's negative 2x over 2y. And of course, we can simplify this just to negative x over y. So what this is saying is, to get the slope of the tangent line at any point on the circle, you just take the x value of the point, the negative of it, and divide by the y value of that point. So it's pretty neat. So it's an expression for the derivative, but it's not just in terms of x, it's in terms of x and y. Let's take this for a spin. Let's see if it actually works. So try out our formula for the point 0, 2. So x is 0, y is 2. What is the derivative for this circle? So dy by dx, or the slope of the tangent line, would be equal to the negative of 0 divided by 2, which is just 0. Now, does this make sense? Go to your unit circle, the circle given here, radius of 2. At that point, 0, 2, is the slope of the tangent line 0. So here's 0, 2. Would you guys agree the slope of the tangent line is 0? It fits, right? Try it for those other 3 points and see if we get results that make sense with the diagram. So here this would be negative 0 over negative 2, which is still 0, which is what we expect, because 0, negative 2 is at the bottom of the unit circle. Very cool. That's part B. That was part A. What about at root 2, root 2? So that is on the circle. The root of 2 squared is 2. the root of 2 squared is 2. And when you add those, you get 4. So root 2 is somewhere right about there for part C. We get negative root 2 over root 2, which is exactly negative 1, which is exactly what the slope of the tangent line is at that point. So very cool how this is all working out. And then this expression even checks out when the slope of the tangent line is undefined. So at 2, 0, where the point is here, and the slope of the tangent line is undefined since it's a vertical tangent line, our derivative still works, because if we take the negative of x, negative 2 over 0, this is undefined. It works. You guys convinced? Very cool. It's called implicit differentiation. So again, it's not part of the high school curriculum, but it's interesting to learn. None of the things we did here are beyond your skill set, so it's just something fun to do, in my opinion. And I run the class, so I get to pick what we do. But we can use implicit differentiation to kind of quickly and efficiently determine the derivative of the natural logarithm function. Now, I did not do this ahead of time, so I'm relying on the last time I did this many years ago, but everything will be fine. What could go wrong when you improvise? To take the derivative of ln x, we don't need to do first principles or do a huge investigation. What we can do is, we don't know the derivative of ln x, but we do know the derivative of e to the power x. And we have this implicit differentiation tool. So let's start by rewriting this in exponential form. Remember, ln x is just log base e of x. So let's write this in our exponential form. The base is e, the exponent is y, and the result is x. That's just taking y equals ln x and rewriting it in exponential form. And now let's use our new tool, implicit differentiation. We'll take the derivative of each side with respect to x. Now the right side is easy. The derivative of x with respect to x is just 1. And on the left side, so what's the derivative of e to the power of y with respect to x? We'll just use the chain rule. The derivative of the outer function is just e to the power of y, because it's e. The derivative of the inner function, well, it's just the derivative of y with respect to x, dy by dx. So rearranging, we get dy by dx is equal to 1 over e to the power of y. But unlike the circle, the ln x is a function, and we can actually get this derivative just in terms of x. Guys, did we not just up here say that e to the power of y is equal to x? So the derivative of the natural logarithm function is just 1 over x, which is a very cool derivative. So dy by dx of ln x is equal to 1 over x. I still think that's fascinating how that comes to be. The derivative of the ln function is just 1 over x. And you can kind of, you can copy this down or not. It's just going to be a rough sketch. If you think about what the ln function looks like, it looks something like this. And the derivative makes a lot of sense. So when x gets really, really, really big, the ln function never quite levels off to the horizontal, but the slope of the tangent line gets more and more and more horizontal, gets close to 0. And when x gets close to 0 here, you're doing 1 divided by a very small number, which gives you a very big number, which makes sense because there's a vertical asymptote at 0, so the slopes of the tangent lines are quite large. So a new derivative for you guys, not one you're required to know. However, I would argue that wasn't easy. It wasn't hard to get there. And yeah, it's just interesting for you guys to know. Now you have that in your back pocket. You guys got a head start on your cohort next year. Now I've got a challenge for you guys. We just did the derivative of the natural logarithm function. Can you guys do this exact same process, but with a base of b, with a general base b? You can just basically copy paste what we did. When you get to the implicit differentiation step, this derivative will be slightly different because we're not differentiating a base of b anymore. It'll be a base of b. I encourage you just to give it the old college try. There's low stakes here. It's just for fun, just a challenge, and I will come along for the ride in a moment. But yeah, just see if you can give it a try. I will pause my recording. So we rewrite an exponential form, and then we're going to use implicit. We're literally copying and pasting, Control C, Control V. Use implicit differentiation. So take the derivative of each side. The derivative of the right side is still 1. And the only kind of new addition here is that when you differentiate b to the power of y, the derivative of b to the power of y, the outer function, is the ln of b. We just have this extra factor of ln b times b to the power of y times dy by dx. And when you rearrange, you get dy by dx is equal to 1 over not just b to the power of y, but ln of b times b to the power of y. And of course, from up above, b to the power of y equals x. So what you get here is that the derivative of a general log function is 1 over x, but scaled by this constant of 1 over ln b. I might write it this way in our conclusion. So the derivative of log base b of x is equal to 1 over x times ln b. I might write it that way. Very cool. Today you learned. So now you guys have that tool in your back pocket for whenever. So that day you guys learn about it in first year calc, you can just sleep in and skip class. No, I would not recommend doing that. You should go to class. Of course, you have the option of pretending the last 10 minutes never happened because I'm not testing you on it, but it was interesting to learn. Anything out of curiosity you guys want to chat about? All right, just thought I'd ask. All right, we're going to end this video.